Welcome to this problem walkthrough for problem number 1224, titled Maximum Equal Frequency. In this session, we'll explore the problem, discuss crucial concepts, and break it down step by step for better understanding. Let's dive in and get started. Here, we are tasked with finding the maximum possible prefix length k in an array of positive integers nums, such that by removing at most one element from this prefix, all remaining integers have the same frequency. A prefix is essentially the first k plus 1 elements of the array, denoted as nums, 0, k. For each prefix, we calculate the frequency of each unique integer within it, which is simply the count of how many times that integer appears. The goal is to determine the largest k where this condition can be satisfied. The input is an array nums with constraints on its length and the range of its elements. The output will be a single integer representing the maximum index k that meets these conditions. In the upcoming examples, we'll see how this works in practice. Let's look at the first example. The input array is nums equals 2, 2, 1, 1, 5, 3, 3, 5. The output is 7, meaning the prefix nums, 0, 7, satisfies the condition when we remove at most one element. In this case, removing the last element, which is 5, results in the frequencies 2, 2, 1, 2, 5, 1, and 3, 2. After the removal, all the remaining elements in the prefix have equal frequencies when grouped as two occurrences of each number except for 5. This makes 7 the maximum value of k for which this condition holds. This example demonstrates how removing a single element can balance the frequency distribution across all integers in the prefix. Now, consider the next example where nums equals 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5. The output is 13, meaning the entire array up to the last element satisfies the condition when removing one occurrence of 5. By removing this element, the frequencies of the remaining numbers become 1, 3, 2, 3, 3, 3, and 4, 3. Here, all elements have equal frequencies of 3. This shows that the maximum prefix length can span the entire array as long as removing one element can equalize the frequency counts across all integers. In the third example, the input is nums equals 10, 10, 10, 10. The output is 4, which is the length of the array. Here, no removal is necessary because all elements already have the same frequency of 4. This is a straightforward case where the array naturally meets the condition, and the maximum prefix length is simply the entire array. Additionally, edge cases like a single element array or arrays where all elements are identical will also fall into this category, as no removal is required to satisfy the condition. For this problem, the solution must be efficient due to the constraints, with the array length and element values going up to 10⁻⁵. This means the algorithm should ideally operate in O(n) time, where n is the length of the array. A common approach involves using hash maps to track the frequency of each number and the frequency of those frequencies. This allows us to quickly check conditions and update counts as we iterate through the array. Efficient frequency counting is key to ensuring the solution can handle large inputs within the given constraints. To solve the maximum equal frequency problem, we first consider a brute force approach. The intuition here is straightforward. For each prefix of the array, we calculate the frequency of each number and check if removing just one number would make the remaining frequencies equal. While this approach is conceptually simple, its implementation involves iterating through all possible prefixes and recalculating the frequencies for each one. This results in nested loops, making the time complexity O(n squared). Given that the input size can go up to 10 to the power of 5, this becomes computationally expensive and impractical for large inputs. Hence, while this method provides a baseline, it is not suitable for solving the problem efficiently. A more optimized approach leverages hash maps to track frequencies efficiently. Instead of recalculating frequencies from scratch for each prefix, we maintain two hash maps, one to store the frequency of each number and another to track the occurrences of these frequencies. This allows us to dynamically update the frequency counts as we iterate through the array. The key observation is that for the array to satisfy the condition of maximum equal frequency, one of three scenarios must hold: either all numbers have the same frequency, all numbers except one share the same frequency while the exceptional number appears once, or all numbers except one share the same frequency with the exceptional frequency being exactly one higher. By validating these conditions incrementally using the hash maps, we achieve an efficient solution. Since each number is processed only once and hash map operations are average O(1), the overall complexity is O(n). This method is both scalable and computationally efficient, making it well suited for large inputs. The optimized hash map solution is selected as the final strategy because it strikes an ideal balance between clarity, efficiency, and scalability. By maintaining running counts for frequencies and their occurrences, we can quickly validate the conditions for maximum equal frequency without recalculating from scratch. The problem is simplified by focusing on a limited set of conditions where the solution is valid, which are checked incrementally. Although this approach requires additional space to store the hash maps, the significant reduction in time complexity makes this trade-off worthwhile. While the implementation is slightly more complex than the brute force approach, the efficiency gain far outweighs this drawback. More complex alternatives, like segment trees or binary index trees, might work but introduce unnecessary complexity. By focusing on the hash map-based solution, we ensure correctness, efficiency, and scalability, making it the best choice for this problem. To solve the problem of finding the maximum prefix length of an array where the frequency of elements meets a specific condition, we need to break down the requirements systematically. The task involves checking if the frequency distribution of elements in the prefix can be adjusted to make all elements appear with equal frequency by removing at most one element. This boils down to evaluating three possible scenarios for any prefix of length k. First, all elements have the same frequency. Second, all elements except one have the same frequency, and that exceptional element appears exactly once. Third, all but one element have the same frequency, and reducing the frequency of that exceptional element by one makes it equal to the others. These conditions form the foundation of the algorithm we'll build to solve this problem efficiently. To implement this algorithm, we rely on two critical data structures. The first is a frequency map, which allows us to count how many times each element appears in the prefix. This gives us the raw counts of individual numbers. The second is a frequency of frequencies map, which tracks how many elements share a specific frequency. For instance, if two elements appear 3 times and one element appears once, the map will reflect this distribution. With these structures in place, we can iterate through the array one element at a time. For each new element, we update the frequency map and adjust the frequency of frequencies map to reflect the changes. Specifically, the old frequency count is reduced, and the new frequency count is increased. After updating the maps, we validate if the current prefix satisfies one of the required conditions, such as having only one unique frequency or two frequencies that fit the criteria mentioned earlier. Once we've updated the frequency maps and checked the conditions, the next step is to update the result. If any of the conditions are met, we adjust the maximum valid prefix length, denoted as max_k, to the current index. This ensures we always keep track of the longest valid prefix encountered so far. After processing all the elements in the array, the final result is max_k plus 1, since arrays are 0 indexed, and we need to adjust for the 1 base length. A few key insights can help us optimize this process. First, tracking the frequency of frequencies allows us to validate each prefix efficiently without recomputing frequencies from scratch. Second, edge cases such as single-element arrays or arrays dominated by one particular element require special attention. For example, arrays like 1, 1, 1, 2, and 1, 2, 2, 2 must be carefully validated to ensure correctness. Finally, arrays with uniform frequencies, such as 1, 2, 3, 4, where all elements appear once, illustrate the importance of handling all possible distributions. Let's take a closer look at the data structures and their role in the algorithm. The frequency map is a dictionary that records how many times each element appears in the array. For instance, if the map is 1, 3, 2, 1, it means the number 1 appears 3 times and the number 2 appears once. The frequency of frequencies map, on the other hand, tracks how many elements share the same frequency. For example, 3, 1, 1, 1 means one element has a frequency of 3, and one element has a frequency of 1. These maps work in tandem to efficiently validate the prefix conditions. From a complexity standpoint, this approach is highly efficient. The time complexity is O(n), where n is the length of the array, as each update to the maps takes constant time. The space complexity is also O(n) due to the storage required for the two maps. These optimizations make the algorithm scalable for larger inputs. To better understand how the algorithm works, let's walk through an example with the array 1, 2, 2, 3, 3, 3. Initially, both the frequency map and the frequency of frequencies map are empty. As we process each element, we update these maps and check the conditions for a valid prefix. For instance, adding the first element, 1, results in a frequency map of 1, 1, and a frequency of frequencies map of 1, 1. This prefix is valid because all elements have the same frequency. Adding the next element, 2, updates the frequency map to 1, 1, 2, 1, and the frequency of frequencies map to 1, 2. Again, this prefix is valid. Adding another 2 updates the maps to 1, 1, 2, 2, and 1, 1, 2, 1, which still satisfies the conditions. At this point, the algorithm continues iterating through the array, updating the maps and validating the prefix at each step. As we proceed further with the example, adding 3 updates the frequency map to 1, 1, 2, 2, 3, 1, and the frequency of frequencies map to 1, 2, 2, 1. This prefix is still valid because it meets the required conditions. Continuing with subsequent elements, the algorithm updates the maps and checks each prefix in the same systematic way. This step-by-step process ensures that we determine the maximum valid prefix length efficiently. By leveraging the frequency map and the frequency of frequencies map, we avoid redundant calculations and maintain an O(n) time complexity. This example illustrates how the algorithm handles dynamic updates and validates each prefix, ensuring correctness across a variety of input scenarios. Here, we start by importing the counter class from the collections module, which will help us efficiently track frequencies. Inside the solution class, the max_frequency method takes an array of integers called nums as input. We initialize 3 variables: frequency, a counter to track how many times each number appears, count, another counter to track how many numbers share the same frequency, and max_len, which will store the maximum prefix length that satisfies the problem's conditions. Next, we loop through the nums array using enumerate to get both the index I and the number. For each number, we first check its previous frequency from frequency. If it has a non-zero frequency, we reduce its count in the count counter and remove the entry completely if the count reaches 0. Then, we increment the frequency of number in frequency and update the count counter to reflect the new frequency. At this point, we evaluate the state of the count counter to determine if the current prefix satisfies the conditions. If count has only one unique frequency, there are 2 possibilities to consider. Either all numbers have the same frequency, or all numbers except one share the same frequency of at least one. In both cases, the maximum prefix length is updated to the current index plus 1. When count contains 2 unique frequencies, we need to evaluate whether the current prefix can still satisfy the conditions. First, we extract the 2 frequency count pairs from count as F1, C1, and F2, C2. Then, we consider 2 specific cases. In the first case, one of the frequencies is exactly 1, and it occurs only once. This means we can remove the element with frequency 1 to achieve equal frequencies across the remaining elements, so we update max_len accordingly. In the second case, the difference between the 2 frequencies is exactly 1, and the higher frequency occurs only once. This scenario allows us to adjust the higher frequency down by 1 to match the lower frequency, ensuring that all elements have equal frequencies. If either of these cases is true, we update max_len to the current index plus 1. Finally, after completing the loop, we return max_len, which represents the maximum prefix length where the conditions of the problem are satisfied. Here, we start with the Java implementation of the solution. We define 2 hash maps, frequency to track the frequency of each number in the array, and count to track how many numbers share a specific frequency. Additionally, we initialize maxlen to 0, which will store the maximum length of the prefix that satisfies the problem's conditions. Now, we iterate through the input array nums. For each number, we first retrieve its previous frequency, defaulting to 0 if it hasn't been seen before. If the number had a prior frequency, we decrement its occurrence count in the count map. If the count for that frequency drops to 0, we remove it from the map entirely. Next, we increment the frequency for the current number, update the frequency map, and add this new frequency to the count map, incrementing its occurrence. At this stage, we check the size of the count map. If there is only one unique frequency, it means all numbers in the prefix either have the same frequency or one of them occurs exactly once. In this case, we calculate the unique frequency and verify if it satisfies these conditions, updating maxlen accordingly. Now, if the count map contains two unique frequencies, we evaluate whether one of these can be adjusted to make the entire prefix valid. To do this, we retrieve the two frequencies and their respective counts. Let's break this into two scenarios. In the first case, one of the frequencies is 1, and it occurs exactly once. This means we can remove the single occurrence of the number with frequency 1 to make the rest of the prefix valid. In the second case, the difference between the two frequencies is 1, and the higher frequency occurs exactly once. Here, we can adjust the single occurrence of the higher frequency to match the lower one, resulting in a valid prefix. If either of these conditions is satisfied, we update maxlen to the current prefix length, which is I+1. This ensures that we always track the maximum prefix length that meets the problem's requirements. Finally, after iterating through the entire array, we return the value of maxlen. This value represents the maximum length of a prefix where, by removing at most one element, the frequency of all numbers in the prefix becomes equal. The approach leverages the two hash maps to efficiently track frequencies and their counts, allowing us to determine valid prefixes in constant time per iteration. With this, our Java implementation is complete. We start by initializing two dictionaries, frequency to keep track of the frequency of each number, and count to store how many numbers have each frequency. Initially, both are empty, and max_len is set to 0. When we process the first number, 2, its frequency increases to 1. This updates frequency to 2, 1, and count to 1, 1, meaning one number has a frequency of 1. Since there's only one unique frequency, max_len becomes 1. Next, when we process another 2, its frequency increases to 2. We adjust count by reducing the count of frequency 1 and removing it, then updating count to 2, 1. Again, there's only one unique frequency, so max_len is updated to 2. When we process the number 1, its frequency becomes 1, updating frequency to 2, 2, 1, 1, and count to 2, 1, 1, 1. Now, there are two frequencies, but no adjustment can make all frequencies equal, so max_len remains 2. Then, the next one is processed, and its frequency increases to 2. This updates frequency to 2, 2, 1, 2, and count to 2, 2. Since all numbers share the same frequency, max_len becomes 4. When we process 5, its frequency increases to 1, updating frequency to 2, 2, 1, 2, 5, 1, and count to 2, 2, 1, 1. Here, two frequencies exist, but since frequency 1 occurs only once, adjustment is possible, and max_len becomes 5. For the next number, 3, its frequency also starts at 1. This changes frequency to 2, 2, 1, 2, 5, 1, 3, 1, and count to 2, 2, 1, 2. Two frequencies exist, but no adjustment is possible, so max_len remains 5. Finally, when we process another 3, its frequency increases to 2. This updates frequency to 2, 2, 1, 2, 5, 1, 3, 2, and count to 2, 3, 1, 1. Adjustment is possible because frequency 1 occurs once, so max_len becomes 7. Processing the last number, 5, increases its frequency to 2. This updates frequency to 2, 2, 1, 2, 5, 2, 3, 2, and count to 2, 4. Now, all numbers share the same frequency of 2, so max_len becomes 8. The final output for this example is 8. Shifting to a simpler input, such as 10, 10, 10, 10, 10, we begin with empty dictionaries for frequency and count, and max_len set to 0. Processing the first number, 10, increases its frequency to 1. This updates frequency to 10, 1, and count to 1, 1, where one number has a frequency of 1. With only one unique frequency, max_len becomes 1. Next, processing another 10 increases its frequency to 2, updating frequency to 10, 2, and count to 2, 1. Since there's still only one unique frequency, max_len becomes 2. As we process the third 10, its frequency increases to 3. Frequency updates to 10, 3, and count to 3, 1, and again, with a single frequency, max_len becomes 3. Processing the fourth 10 updates its frequency to 4, with frequency becoming 10, 4, and count as 4, 1. The unique frequency ensures max_len is 4. Finally, the fifth 10 increases its frequency to 5, updating frequency to 10, 5, and count to 5, 1. The single frequency results in max_len becoming 5, and the final output for this example is 5. Now consider the input 1, 2, 3, 4, 5, 6, which contains all unique numbers. Initially, frequency and count are empty, and max_len is 0. Processing the first number, 1, increases its frequency to 1, updating frequency to 1, 1, and count to 1, 1. With only one unique frequency, max_len becomes 1. For the second number, 2, its frequency becomes 1 as well, updating frequency to 1, 1, 2, 1, and count to 1, 2. Since all numbers have the same frequency, max_len becomes 2. Continuing, processing the third number, 3, also gives it a frequency of 1. This updates frequency to 1, 1, 2, 1, 3, 1, and count to 1, 3. With a single frequency, max_len becomes 3. The fourth number, 4, similarly gets a frequency of 1, updating frequency to 1, 1, 2, 1, 3, 1, 4, 1, and count to 1, 4, resulting in max_len becoming 4. Processing the fifth number, 5, updates frequency to 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and count to 1, 5. The single frequency allows max_len to reach 5. Finally, processing the sixth number, 6, updates frequency to 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, and count to 1, 6. With all numbers still having the same frequency, max_len becomes 6. The final output for this example is 6. The time complexity of this algorithm is O(n), where n represents the length of the input array nums. This efficiency stems from the way the operations are structured. First, the algorithm iterates over the array using a single for loop. Since each iteration corresponds to one element in the array, the contribution of this operation is O(n). Additionally, during each iteration, the algorithm updates two hash maps, frequency, which tracks the frequency of each number, and count, which tracks the count of those frequencies. Updating a dictionary key in Python is an O(1) operation on average, and since we perform this update once per iteration, the total contribution of these updates is O(n) as well. Together, these steps ensure that the algorithm processes the input array in linear time. To determine if the current prefix satisfies the problem's constraints at each step, the algorithm evaluates the count dictionary, which contains at most 2 keys. This involves checking the length of the dictionary and performing straightforward comparisons and arithmetic operations, all of which are constant time tasks. Each of these condition checks contributes an O(1) operation per iteration, so across all iterations, this step also adds up to O(n). When we sum up the contributions from array traversal, counter updates, and condition checks, we see that the total time complexity of the algorithm is O(n). This linear time complexity highlights the efficiency of this optimized approach, as it minimizes redundant calculations and ensures that each element is processed only once. The space complexity of the algorithm is governed by the additional data structures used, specifically the frequency and count dictionaries. The frequency dictionary tracks the frequency of each distinct number in the array. In the worst case, where all elements in the array are unique, frequency will contain n entries, leading to a space usage of O(n). Similarly, the count dictionary tracks how many numbers share the same frequency. The number of distinct frequencies is bounded by the maximum frequency of any number, which cannot exceed n. Thus, the space usage of count is also O(n) in the worst case. Finally, the algorithm requires only a constant amount of space for intermediate variables such as max_len, I, and number. This constant space usage does not scale with the size of the input, so it contributes O(1). Together, the overall space complexity is O(n). When we sum up the contributions to space complexity, both the frequency and count dictionaries dominate, resulting in a worst-case space complexity of O(n). Comparing this optimized solution to a brute force approach, the naive method would involve recalculating frequencies from scratch for every prefix of the array. This would result in a time complexity of O(n squared, as it performs redundant calculations for each prefix. In contrast, the optimized approach uses counters to maintain frequency and count information incrementally, reducing the time complexity to O(n). Both approaches share the same worst-case space complexity of O(n), however, the optimized approach is more memory efficient in practice because it avoids redundant recalculations, leveraging hash maps to ensure efficiency. The time complexity of the optimized approach remains O(n) across the best, average, and worst-case scenarios. In the best case, the algorithm processes each element exactly once, achieving linear time. On average, the operations per iteration remain constant, maintaining the O(n) complexity. Even in the worst-case scenario, such as when all elements in the array are unique, the algorithm does not exceed O(n) time complexity. This consistency is due to the use of hash maps for efficient frequency and count tracking. In conclusion, this optimized approach is far more efficient than a naive solution, achieving linear time complexity by avoiding redundant calculations. Its space complexity, while also O(n), is well controlled, making the algorithm suitable for handling large inputs effectively. When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases like small arrays or arrays where all elements are the same can cause issues. For example, if the array is empty or contains just one element, your solution might fail due to divide by zero errors or incorrect assumptions about frequency distributions. Similarly, if all elements in the array are identical, you might misinterpret the conditions for maximum equal frequency. Another pitfall is implementing a brute force solution that recalculates frequencies from scratch for every prefix. This leads to redundant computations and an inefficient O(n squared) complexity, which won't work for large inputs. Additionally, many misunderstand the maximum equal frequency condition. Instead of ensuring all elements have the same frequency, the goal is to allow at most one frequency to deviate by 1 or to have one element with a frequency of 1. Mistakes also occur in updating frequency maps. If you don't correctly decrement the count of the old frequency before incrementing the new one, your frequency tracking will be inaccurate. Finally, overcomplicating the solution with unnecessary loops, multiple hash maps, or excessive data structures can make debugging and maintenance much harder. Always aim for simplicity and clarity in your approach. Now, let's consider how this problem is approached in interviews. Efficiency is a key focus, and interviewers often expect you to optimize from a brute force O(n squared) solution to a linear O(n) approach. To achieve this, you can use hash maps to dynamically track frequencies and their counts as you iterate through the array. It's important to think incrementally rather than recalculating everything from scratch. Focus on how adding or removing an element affects the current frequency distribution. Interviewers also value candidates who demonstrate attention to detail, so proactively mentioning edge cases, such as empty arrays or arrays with identical values, can make a strong impression. Another important skill is recognizing patterns in the problem. Specifically, you need to understand that valid states allow at most one deviation in frequency counts. Developing the ability to quickly identify and articulate these patterns during the interview can set you apart from other candidates. This problem also shares similarities with other problems that might help you build intuition. For example, LeetCode 904, Fruit into Baskets, involves a sliding window technique and frequency counts. Similarly, LeetCode 159, Longest substring with at most 2 distinct characters, uses hash maps to track frequencies, which is a valuable skill for this problem. LeetCode 697, Degree of an array, focuses on frequency and ranges, while LeetCode 340, Longest substring with at most k distinct characters, is another frequency tracking challenge involving hash maps. Exploring these problems can deepen your understanding of related patterns. Beyond that, there are alternative approaches to solving this problem. A sliding window optimization reduces redundant calculations by maintaining a valid window of prefixes. However, this method requires careful handling of hash maps to ensure correctness. It has a time complexity of O(n), but the space complexity may be higher due to the use of hash maps. Another approach is prefix sum with frequency tracking, where cumulative changes in frequency are analyzed. While this method can provide insights, it's often harder to implement dynamically compared to the sliding window approach. Finally, let's touch on the brute force approach. While simple to implement, this method involves calculating frequencies from scratch for each prefix, which results in an n² time complexity. This can be helpful when verifying correctness for small inputs or when you're just beginning to understand the problem. However, for larger arrays, this approach becomes impractical due to its inefficiency. While brute force can serve as a stepping stone, it's essential to move toward optimized solutions for real-world scenarios and interviews. Great job reaching the end of this walkthrough on the maximum equal frequency problem. We covered how to use hash maps for frequency tracking, reviewed time and space complexities, and discussed critical takeaways. Don't forget to practice similar problems, and I'll see you in the next session. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!